Good morning, everyone. Hello, and thank you for taking the time to join us today as we discuss quality of methodology related to the FSA sections of uh, FAR 450. My name is Luis Estrada, and I'm a flight safety analyst, the flight safety analysis branch, that's ASA 210. And I'm honored to be your presenter today, and we'll be answering questions along with Dr. Larson, who is the senior technical advisor in the ASA 200 division. He's got decades of experience in flight safety analysis and has written a lot of the methodology of the FSA guidelines that we have published and that is available to you for use. And we rely on him a great deal. I need to inform you that this presentation is being recorded and may be posted in a public domain in the near future. With that said, the purpose of this methodology workshop is to provide further guidance as to what AST expects with regards to methodology descriptions under the umbrella of 450-115C. Our intent with this is to help applicants minimize the amount of submissions needed to get a methodology to meet 450 compliance. There are going to be 3 sections to this workshop. The first section provides context to 450-115C requirements. The second section includes explanations of 450-115C elements with examples, highlighting specificity, the level of rigor, detail, and content for the FSA portions that constitute a well-written section of a methodology. Unfortunately, due to the time constraints in the medium of this workshop, we cannot go over the entirety of a methodology description that meets the regulation, but we intend to provide you with a window into what we expect to see in terms of detail by referring to small portions of a methodology. And finally, the third section introduces a checklist for description of methods, highlighting an example that addresses key discussion topics that we normally expect from a methodology description. We will go over some of those key topics in an example for POF, that is 450-131. At the end of each of those 3 sections, there will be an opportunity to ask questions. Please use the Q&A function to ask your questions, or in the chat, you can place those questions. We will answer as many questions as time allows. Any questions we do not get to answer during the workshop would be answered after the workshop in writing or at the next FSA office hours, which is, I believe, next Friday. Please consider any verbal guidance or answers to questions that we provide in this medium as preliminary and subject to change, as we are responding to you without full consultation of FSA and the AST team. We'll go now to section 1, which is the context of 450-115C. As you may recall, Part 450 came about after a great deal of work on the part of industry and from FAA's team of engineers, attorneys, and licensing team, and rulemaking staff, as well as government partners. This new regulation consolidates the rules for expendable launch vehicles, reusable launch vehicles, and re-entry vehicles into one performance-based rule for vehicles. It allows for a single license to authorize multiple sites and was developed to minimize duplication with our government partners. This performance-based regulation is primarily intended to provide industry a greater level of flexibility to develop means of compliance, what we know as MOCs, that maximize objectives while maintaining public safety. The key shift in Part 450, as you may have noticed from previous regulation, is that the safety analysis aspects of the license have shifted from a focus of products to a focus of methods. This allows for more flexibility in the approaches and level of analysis effort an applicant can choose from. For instance, as noted in the slide, a license modification will not be necessary for the new flight azimuth or the new launch site, provided that the assumptions of the means of compliance, the methodology proposed on the original license are still valid, and the applicant's process accounts for any updates to the analysis as a result of any variable inputs such as wind profiles, probability of failure, exposed population, and variable flight rules. But the amount of initial analysis and documentation to get there and the amount of effort may be greater than if the applicant was to fly a single mission profile from the same launch site. Means of compliance is the approach that is used to satisfy a section or a subsection of the regulation. Those every requirement has a means of compliance, and for 450.35A, the administrator must accept that means of compliance. Because of the nature and complexity associated with means of compliance, they need to be accepted prior to application acceptance. So we have identified six types of acceptable means of compliance for flight safety analysis. Type 1 is advisory circulars, or what we call ACs. ACs help industry and support license application process in two ways. The first is intended to provide a means of compliance. Thus, if you follow the relevant AC precisely, providing a healthy amount of detail, you will have met that requirement. The second way is that it helps industries to further explain the meaning of the regulatory text by discussing intent and goals of the performance-based regulation requirements to help you comply with that intent of the reg for your particular situation. This provides you an opportunity to use ACs as guidelines and allows you to tailor to your particular scenario and process. But it will then become a type 5 MOC that the FAA will need to evaluate. It's no longer a type 1 because the AC is not followed precisely. Now, type 2 MOC is a standard that has already been accepted by the FAA administrator. That is something that the FAA has evaluated and accepted as a means of compliance. Those are publicly available and are maintained on our FAA website, and the link is in the slide. And just like with the ACs, for you to get credit for using that means of compliance, you must follow them precisely. Otherwise, just like with the ACs, you could use them as guidance and tailor to your specific process. And then it becomes a type 5 MOC that we will discuss in just a few minutes that the FAA still needs to evaluate. Type 3 MOC in this list are services provided by a federal entity. The FAA works with the federal branches to help approaches and methods and standardize those methods through the CSW group. And for 450.135B, the FAA will accept their flight safety analysis as long as the FAA has reviewed and accepted the processes for that site, and to the extent that the analysis meets our FAA requirements. The service for which federal entities have been cleared to provide would be specified in detail in a MOU between the FAA and the federal branch. However, no federal entity performs all of the flight safety sections, and there will still be additional FSA documentation that the applicant will be responsible for, such as the input data needed to begin that analysis by the federal branch and associated methodologies to derive those inputs. as well as data required in order to continue processing the license, such as data necessary to perform a maximum probable loss determination, for instance, or a specific data associated with pre-flight reporting under 450-213. Type 4 MOC is a safety element approval under 450-39. And it relates in our discussion to flight safety analysis to those services that someone or an entity, such as a contractor, may provide. And it is dependent on the FAA acceptance of the proposed safety standard for the particular element in question. Currently, there has not been yet a safety element approval for 450 FSA requirements. We hope that that changes in the future. And now type 5 MOC is the applicant's specific description of methods. This is where an applicant makes a case that their methodology, whether that is tailored from a standard or an AC, meets the requirement as established for each flight safety analysis section and each flight safety analysis subsection of the regulation. The methods need to be accepted during the pre-application consultation process prior to application acceptance. This is very important. Due to the nature of the complexity of the flight safety analysis methodology, this approach usually takes longer time to evaluate than the other type MOCs, from weeks to months of iterations between applicant and ASD to get to a level of compliance. And lastly, the last means of compliance is the applicant providing actual mission data as representative inputs into a flight safety analysis. The evaluation of this FSA happens via an independent analysis by the FAA. This approach may be faster than type 5 to get a license approved, but comes with some restrictions, as it would only be applicable for that mission profile and those conditions that were analyzed through our independent analysis. The FAA may still require additional products for the purpose of performing that independent analysis, as stated in 450-45E7. If an applicant, here's a note, caveat, if the applicant decides to use a previously accepted MOC or an AC, the FAA reserves the right to determine whether an applicant can reasonably use that standard based on consistency with all the conditions of that accepted means of compliance. And if the application demonstrates a method that exactly follows that accepted means of compliance or AC. So what is a methodology? The methodology is a structured procedure of principles and rules for bringing about a certain goal. In flight safety analysis, it refers to the systematic, planned, structural, and repeatable process that results in an analysis that applicant performs to achieve a level of fidelity appropriate to demonstrate that a given operation meets the safety criteria. It captures development of input data and the scientific principles used in the analysis, that is qualitative and quantitative descriptions of analytical model used to approximate real life, as well as the assumptions and justifications guiding that analysis, with a rationale why the proposed approach is appropriate. Of course, no analytical model will be complete without a validation or verification of the outputs or the process. Outputs which may be used to develop risk mitigations back into the process. The call out for methodology in the FSA sections of the regulation is with the statement descriptions of the methods of, which refers to those explanations used to comply with the sub-analysis fundamental purpose, constraints, objectives, which are typically followed by data requirements. The purpose of the objective and constraints descriptions of the FAA sections lay the foundation of that methodology. So it's important that your methodology addresses those directly. All descriptions of the methods statement refers back to 450.115C, which sets the standard for the methodologies used in FSA over the life cycle of the proposed license activity. And we will talk more about 450.150C in a couple of slides. Now this slide depicts flight safety analysis components for which there is a requirement for methodology descriptions, and for which the standard under 450.115C apply. Starting from the moment of liftoff, 450.117 methodology describes how normal trajectory analysis is employed to derive the nominal uncertainty and variability trajectories that bound the limits of normal flight. Any deviations of the vehicle outside of the normal flight will be covered under 450.119 malfunction trajectory analysis, which estimates that deviation capability and attempts to capture those trajectories that may still be useful for the operation, and the behavior of those that are failures that are not capable of meeting mission objectives and may hazard population. 450.131 addresses the systematic procedure for determining the probability of failure of the vehicle and how that probability is distributed to the failure modes used in 450.119 that were derived from a functional hazard analysis, and how that distributed POF is allocated to the phase of flight. A hazard control strategy typically uses a flight safety analysis in terms of a flight abort. This is covered under 450.108, which lays the objective that an applicant must determine flight safety limits that define when an operator must initiate flight to abort to prevent continued flight from increasing risk to population. Once a vehicle has failed, and there are a few possible culmination scenarios, most which lead to vehicle breakup. That is aero breakup, aero thermal demise, FTS destruct, or an intent impact. This is covered under 450.121 breakup analysis, where the applicant needs to describe the methods used to determine the end states and resultant debris characteristics, as well as the propagation of that debris field and probability distribution at impact. But debris may not be the only hazard. Toxic fumes emanating from components, payloads, or propellant may be possible. Under 450.139, a toxic release analysis is required for any toxic chemical on board a launch or re-enter vehicle. Likewise, distance focus over the pressure under 450.137 may be another hazard. The applicant may need to provide descriptions of the methods used to quantify the risk to population. Another important input into the flight safety analysis is the population exposure under 450.123. This is the procedure the applicant establishes to acquire population data and determines vulnerability to individuals. This is critical importance, as this is the population that we are trying to protect. 450.135 brings all the inputs together previously developed under the mentioned methodologies and models casualty area, and computes the predicted consequence of reasonable foreseeable failure. It determines casualty expectation to include individual risk and conditional risk that are later compared to the risk safety criteria. And lastly, 450.133 flight hazard area analysis is a risk mitigation strategy that determines how keep out areas are computed for land, air, and sea, and identifies any region that must be surveyed, published, or controlled, or evacuated. Slide 9 discusses 450.115A and B and 45101G. This is the scope and level of fidelity. In the previous slides, we discussed briefly components that are crucial in flight safety analysis. The scope and level of fidelity of that analysis is governed by 450.115 and 450.101G. 450.115A states that an operator methods must account for all reasonable failures of the critical system during the operation that could jeopardize public safety. It sets the standard for scope to reasonable, foreseeable hazards and hazardous events. Here, foreseeable means that the failure event is identifiable and derived from a functional hazard analysis of a well-established system safety process that includes previous failures that could jeopardize public health. The resolution accounted for in the analysis is set by the level of fidelity necessary to comply with 450.115B, which needs to be sufficient to demonstrate that it satisfies the safety criteria, accounting for all levels of uncertainty, identifies what the dominant source of risk is, and includes a use of mitigations and uses accepted methodology by the administrator. 450.101G addresses validity of the flight safety analysis to demonstrate compliance with 450.101 by requiring use of accurate data, acceptable scientific principles, and a statistic valid approach, producing results that are consistent with or more conservative than the results available from previous mishap tests or other valid benchmarks, or a higher fidelity method. All of the FSA sections must use methods that comply with 450.101G because they are essential to demonstrating the compliance with the safety criteria. Next slide, please.
Yeah, I'll add on that 101G, that is the core sort of standard for how good, what do we say, when is the methodology valid? And it's this, accurate data, accepted principles, and statistically valid. These are the, what is a good enough, 115C talks about what needs to be covered, but 101G is the standard for what is good enough here. So that's how you're going to see, that's what we're trying to get to, is to what is enough there to demonstrate that satisfaction of 101G for all of the elements of 115C.
Thank you, Dr. Larson. Slide 10, I believe it's like slide 10. Description of the methods for 450.115C. How do you demonstrate scope and fidelity in 450.115A and B? You do that through 450.115C, which is the application requirements of section 450.115. And it says the standard for FSA methodology. It requires an applicant to submit a description of the flight safety methodology, including identifications of scientific principles and statistical methods, all assumptions and the justifications, the rationale for the level of fidelity, and the evidence for validation and verification required by 450.101G, the extent of any benchmarks performed, and the extent that risk mitigations were accounted for in the analysis. These requirements apply to all of the 10 sections of FSA that I have previously mentioned, from fly aboard to normal trajectories, malfunction to probability of failures, toxic, DFO, population, risk analysis, and flight hazard development. In FSA methodology, the FSA methodology is where you tell the reader exactly how you design your analysis and how you, and just as importantly, why you did it this way. You comprehensively describe and justify all the methodologies choices made in your analysis. Is where you describe your approach, what data was collected and how it was collected and how you analyzed it and the steps that you took to come to the conclusion that you're presenting to the FAA. It has to have the same similar texture and color as you write a dissertation, a thesis, or a technical report, and should address content, rigor, and depth. The content should address each element of the subject analysis, in particular, the essential constraints and objectives that correspond to the performance-based requirement, as well as other application requirements with a scope and level of fidelity sufficient to comply with 450.115A MV. It should cover all 6 elements of 450.150C, which we have just discussed, and it should explicitly describe the intent, usage, and coverage of the method and any of its limitations. The rigor of the description is more about quality than quantity. It focuses on the conceptual understanding that the methodology describing is trying to establish. It is important that the logic is clearly described, that is based on generally accepted approaches with specific references that are readily available to the reader, that the mathematics are well integrated with the narrative and are complete, that there is comprehensive description of the evidence presented to us to support a claim, such as any validation, verification, benchmarks, and the depth of the detail refers to the level of specificity or completeness of the description. It should be sufficient to be objectively verifiable. An evaluator or a reader with the necessary specialized tools and the training using those tools and using the same inputs, following the same approach, should be able to reproduce consistent results and derive the same conclusion as posted by your analysis. It should be inspectable. Any statements that you made could be clearly supported by evidence upon request of the reader or evaluator. And it should be repeatable. 2 different engineers looking at your method description will not interpret them differently in a significant way. Now we come to a example of level of content, rigor, and depth. This slide has a sample highlighting a deficiency in the level of specificity of a complex concept. We have gotten submissions where a complex process is defectively described in simple terms. And this made-up example, a description of the repropagation is defined in 1 sentence, well, without any reference to the governing mathematics or integration of the equations of motion, and is unacceptable. The applicant states that they're using a 3D propagator that incorporates some environment conditions using their in-house tools and nothing more. This is an unacceptable submission as it leaves very little for us to work with and evaluate. And we will need to be able to find, we will not be able to find any compliance with a corresponding regulation with a single line like this. What we need to see is a dedicated section to those concepts or processes that have significant effect in the computation of risk or in development of risk mitigations that maps to the reliable references and contains descriptions of the mathematical functions and models and inputs. We do not need to see the basic fundamental operations like matrix multiplication, but only those functions that provide a conceptual understanding of the approach being put forth. It also needs to declare assumptions and provide some sort of validation to increase the confidence in that approach. In this example, the acceptable summation has description of the input data, that is position, velocity, and beta. It contains a reference to an atmospheric model, which we can verify, and a reference to an Earth model that is widely used in the industry, and to equations of motions and how they are integrated with respect to time using Runge-Kutta method with an error predictor and corrector that has reference that we can review to learn how error is being handled in the integration. And any assumptions made to facilitate the functionality of the propagation and the expected output of the process. In this case, that expected output is the time, position, and velocity. So we have inputs, we have the process, and then we have the output. Please note that this is an extremely brief version, and we would be expecting a higher level of detail from an actual summation. But I think this gets the idea across of what we were expecting as an overview.
So Luisa, I just want to correct, we don't necessarily need a higher level of detail. This is very brief because it references sources that actually have all the math. We've also gotten submissions that just present all the math. So rather than saying, you know, it's a referencing one reference one where you have a 3 degree of freedom equations in motion, it actually lists all the equations of motions and how, you know, you're incorporating all the forces into that. So I'm trying to point out here that it really can make it, you can be very precise and specific if you're by using external references. And obviously that's going to make it also faster for us to evaluate. If you give us, you know, a lot of equations that then we're going to have to go, you know, look at or review and evaluate. Well, if you present something that's actually an accepted external source that's widely used, that's going to be a lot faster for us to say, yeah, that's actually something that we can look at and very quickly evaluate and say, yeah, that's a solid source. And if that's the requirements for implementing in your algorithm, then that's excellent. That's a very clear way to present, but it also keeps your documentation short, concise, but as you say, this is inspectable, it's repeatable. You know, the goal, hopefully, I think somebody picked up this one and went to these references, they could reproduce an algorithm that has no meaningful differences from the algorithm that you wrote from this description.
Good point. Thank you, Dr. Larson. I think that's the end of the section.
Yep.
Okay. Any questions? I guess they're on the chat. Do you mind reading them, Dr. Larson? I don't.
Yeah, the only question we've had so far was whether we could, we plan to distribute these slides, and the answer is yes. It won't be right away. We want to make, there's some more, you know, any corrections that we make today, and we want to do a final check with legal before we distribute the written versions, but we do expect to send it out.
That is correct. There may be some changes after our discussion here.
Oh, questions? Did you chat or speak? Whichever one you think is easier, I think, for you. So we're open. Okay, so
okay.
Can you do Cleveland? Can participants unmute themselves? I don't know.
Yes.
Okay, so somebody asked, you know, rather speak verbally. Go ahead, unmute yourself and go ahead and ask the question.
Hi, my name is Greg Mahalik. I'm with the Aerospace Corporation. I just want to check to see if you can hear me.
Yes,
right
you can. Thanks, Greg.
Okay. Yeah, my question is on the I forget what are the subpart. One of the subparts talks about potential impact to airborne aircraft, right, of debris.
Right.
And you know, the assessment of what's the likelihood and probability and risk assessment of the debris from the launch vehicle hitting the aircraft, right? So I'm wondering, does there need to be a second assessment of if the debris hits the aircraft and the aircraft comes apart as a result, where all of that debris lands on the ground? Or is it just the probability of the debris from the rocket hitting the aircraft? Do you follow?
Secondary effects are, so that's an interesting question. I would say it has not, I mean, this is really more technically specific. We might answer this more in an office hours. The incorporation of secondary effects is an interesting topic. Traditionally, they have not been incorporated usually there's very small contributor. I mean, I'll say for aircraft risk, the aircraft risk is almost all entirely driven by small fragments that don't cause the aircraft to break up, but directly cause casualties to people on board.
Okay, yeah, thank you. I was just,
Yeah.
if there is some part that hasn't broken up quite yet because it is still at altitude and it hits an aircraft that's full of people,
Yep.
then there would be likely, some pretty substantial secondary effects, I would think, right? But the probability of that happening is, I guess, what has to
Right. Yeah. The
Okay,
probability of an intact object typically hitting an aircraft is usually very small. So it's when you already have breakup, that's what drives almost all the aircraft problem.
Understood. Thank you.
Okay, so there's another question in the chat. How do we know exactly what sources the FAA will accept for analysis purposes? Will this be provided with feedback? And this is again where we're looking, we don't have a list of sources that are valid sources, something that has been peer reviewed and is generally accepted, that has evidence behind it. That's going to be something that it's going to be much easier to for us to accept and find. I mean, for example, for normal trajectory simulation, there are tools out there that have been widely used in industry, like POST, and that's a great an excellent source. We know that it's out there. We know that it's got that history out there. As you say, if there's something that you present that is less well known, we may ask for it. We may need to get more detail on that to review it and see what the foundations are. But it should get back to, should be clearly derived from generally accepted physics and chemistry, if as appropriate, that can be used. That what is generally accepted in the scientific field that we're studying, or in the engineering field, it should be clearly derived from that. And if the tool's already out there and is common within the field and been accepted and being, we understand the history of it, the history of that method, then we're going to accept it. There's that list, I think, of things that we accept could be quite extensive. We do want to work in the ACs at providing even more specific references to things that are acceptable or are useful references on that front. Does that was a question from Andrew. Hopefully that answers that question.
Okay, so if there are no questions, we can keep going to the next slide.
Said a couple more on
Okay.
the one of the early slides. You mentioned the intent of 450 is to allow methodologies to apply such that an applicant wouldn't need a license modification to do a new flight azimuth or a new launch site. Can you clarify if you mean specifically from the flight safety perspective, or is the intent that really no license modification at all is needed to add in a launch azimuth or a launch site?
Yeah.
So I would say the intent of 450 was to be an operator's license. There are things that you would need to put in there. I think there's certainly some policy reviews that are dependent on the environment to some degree. So certainly interactions with foreign countries is something that the State Department, it's hard to say that, okay, you can just take this to another launch site and do a completely different trajectory that potentially has different foreign policy implications. So there are limits on that, but certainly to the extent that's possible. And we're focusing on the flight safety analysis, of course, that we really do want to get methodologies that could apply to different launch sites. As we'll get into later, though, some launch sites, because of their environment, will need a higher fidelity, because the mitigations that work at a remote launch site don't work at a site that has a lot of, has much more around it. So it's not necessarily that, oh, well, this methodology works for any launch site. this methodology works for a class of launch sites for which these mitigations are practical.
Right. And if that launch site wasn't in the initial license application, there would still need to be a modification to add it in.
As I say, I wouldn't say that's necessarily true. You would need to submit the data, and it would need to be clear that your approaches were, that if you can follow the same approach and produce mitigations that are workable in that environment, it wouldn't, I don't see that it would necessarily be a license modification. Now,
Well,
we
again,
haven't gotten to
you're
that point.
thinking flight safety, but
Yeah,
you know, if someone doesn't have an environmental assessment for a new launch site, they need a license modification.
that's right. Yes.
I just don't want people to take away from this that they
Right,
don't need
good
license
point. Environmental is another case where, yeah, you need, that is true, so. The safety analysis side, I think, is we're aiming to get methods that can all work for the safety analysis side, yeah.
Awesome, yeah. And then on the different types of means of compliance, I thought type 6, the actual mission data, was really interesting. Is there an example FAA could give of a type 6 means of compliance where someone's using actual mission data?
Well, yeah, I'm not going to talk about any particular applicant. This is something that we've been recently working to implement. This is really designed for somebody who's doing an initial test flight, and we're trying to help. We see that type 6 is intended. We want to do a test flight. We don't want to have our, go through make sure that our methodologies are fully rigorous. We're going to submit products, and what the FAA will do is assess the products to show, okay, the methodology works for this particular mission. What we see there is that's going to work if you can accommodate, like it also requires that all of your, basically in like 135A, there's two options: that you do a countdown analysis, or that you do encompass all foreseeable conditions. Well, if you're going the route of that, this is actually what we're going to do, you have to use the all foreseeable conditions. So you end up with typically larger hazard areas, more significant mitigation. So that ends up with more operational restrictions. It's also, we're only going to be able to do independent analyses for any one operator at a certain rate. We're probably wouldn't expect that we'll be able to do more than 3 or 4 a year. So if you're moving to an operational cadence, that option no longer becomes valid. But we're trying to enable operators to do initial test flights without necessarily needing to go through the entire methodology process that would allow them to do multiple missions without coming back for a license mod.
I see. Okay, this is slightly different than what I thought it was then. This is a more targeted version of a compliance acceptance. It's not saying, hey, I have these 50 flights of data and therefore I can meet 117 because I use these 50 flights of data to prove that I can do trajectory analysis.
Yeah.
Okay, thank you for that clarification.
Sure, yeah.
One other question. Do we need to validate that our specific implementation is correct, or is it enough just to talk about the methods that it's based on, like WGS 84 or something like that?
So we will be talking about the V&V. So that does come up in the V&V, that your implementation of that needs to be verified. So yes.
Great, thanks.
Yeah. This example was specifically talking about, the example we put up there was the C1, was really just covering the scientific methods and statistical methods for how this was going to be implemented. But they're separate. The C4 requirement talks about V&V.
Great. Thank you, Dr. Larson.
Sure. Other questions?
Yeah, one more on the 101G. I understand the requirement to use accurate data, scientific principles, and have statistically valid results. But when it comes to being consistent with or more conservative than mishaps tests or higher fidelity methods, how is the 101G criteria evaluated if you are trying to, say, remove conservatism from the current high fidelity model? I know an example that we went through a couple of years ago was
Yeah.
removing conservatism from the glass shard hazard model. And so that actually produced results less conservative than the current highest fidelity model.
Right. So that would be, you had data to support that. So that can be at a submodel level where if there is, empirical data to back that, then that's how that particular model can be benchmarked. So it's not necessarily it's not benchmarked against the current necessarily the highest fidelity model that's currently being used for flight safety analysis. It could be certainly a modeling that's higher fidelity that's from another field, or it could be based on empirical data, just like any science is advanced through, validating theories with empirical data.
Copy. Okay, thank you.
Yeah. Okay, let's move on because we do have a lot of more material here. I think that would be helpful.
All right, so we're going to go into section 2. In this section, we will provide further discussion of the 6 elements of 450.115C with some examples. We will discuss elements C1, 2, and 3, and then show an example based on a fictional submission of a submodel of 450.117. We will do something similar with C4, 5, and 6 with a different example. We will start out with C2, assumptions and justifications, and follow on with C1, scientific principles, as that order operation makes a little more logical sense. Next slide, please. So what are assumptions? Assumptions are beliefs based on previous experience, are things that are expected to happen or circumstances that are accepted as true, that are often necessary to simplify problems and set limits to an analysis. It is important to understand what the assumptions are for any process modeling method, because the validity of these assumptions affect whether or not the goals of the analysis will be met. We find that there are 3 types of assumptions in flight safety analysis methodology. The range of applicability or scope for which the methodology is intended to cover and not cover, that dictates the circumstances under which the method and procedures are allowed. Assumptions that are made about physical phenomena to make a problem more manageable and easier to model, such as assuming that interconnected bodies under the action of external forces do not deform like in a rigid body code. Assumptions about the physics included in the code that limit the applicability of the simulation. An example is the assumption of a lump mass, for instance, of a debris fragment, which is acceptable in cases when the vehicle is not designed to withstand high loading and has readily demised materials, but not suitable for complex or high mass structures. And lastly, a statistical model involving terms relating to random errors, assumptions that may be made about the probability distribution of these errors. A few of the most common assumptions in statistics are normality, linearity, uniformity, and in some cases, equality of variance. As mentioned, it is important to understand what the assumptions are for any process modeling method, because the validity of these assumptions affect the result. It is also very important that in your documentation, that assumptions be stated clearly at relevant points within the narrative. We find it very helpful and makes our evaluation more effective when these key assumptions and their justifications are summarized in a table or a matrix. 450.115 C1, that is scientific principles and statistical methods. This is about the use of approaches grounded in theory. It begins with an overview of what clearly describes the integration of different elements of the modeling and submodels. This is usually accomplished by the use of diagrams and flow charts, like data flow diagrams, and the link between overview and elements should be obvious to the evaluator or the reader. Each of the submodels should be based on established scientific principles. That is, ideas based on scientific rules and laws that are generally accepted by scientists or engineers, as well as standard statistical methods using collecting and analyzing data and or empirical data. Scientific principles refer to the knowledge base on the scientific method, such as those established in the fields of physics, chemistry, and engineering. In contrast, a statistical valid analysis is the extent to which drawn conclusions of an analysis can be considered accurate and reliable from a statistical sense, and is the result of sound application of mathematics and accounts for the uncertainty due to sample size limits, the degree of applicability of the data to the system, and similarity of the data. And the level of detail should include equations and not examples that drive the conceptual approach of the methodology, but not the algorithms implementation or code. Standard mathematics like linear algebra, calculus can be assumed and does not need to be shown in a description. If you choose to use a off-the-shelf software, it is imperative that you provide references to the technical manuals and have them readily available to AST in case we request them, or provide some assistance in order to obtain them. 450.115C3, the rationale for the level of fidelity. This relates to the accuracy or degree of exactness of the process or the model or simulation when compared to the real world. As discussed previously, for 450.115B, considering the amount of uncertainty that the approach brings to the results, it needs to have the sufficient dependability to establish with a high level of confidence that the compliance with the safety criteria is achieved. Fidelity is, in other words, a measure of the bias and uncertainty in your process model. Therefore, documentation should discuss each submodel and input data and how sufficient the fidelity was found. It can be done quantitatively. For instance, if your model design is simplified to run more quickly or require less analysis, measuring of bias and uncertainty could be achieved via comparison to a higher fidelity model or higher set of fidelity data. In some cases, a qualitative approach is more appropriate. This applies to bias and uncertainty, which does not have supporting data within the analysis, but instead has an estimate based on outside knowledge or an engineering judgment. Perhaps the calculation has been performed multiple times that you have evidence that the prediction is conservative, overestimates the value that you're trying to predict a high percentage amount of the time. In either approach, the discussion is necessary that explores and quantifies how the uncertainty affects the fidelity of the overall results in context to the risk analysis, particularly the values that are used to comply with the safety criteria. This slide is a continue of our discussion of rationale for the level of fidelity. The highlight of this slide is the operator's decision for accuracy of process and modeling approach and costs. High fidelity approaches are usually more costly as it requires a higher level of effort from the applicant to develop the approach, to develop those input data, as well as it requires a lot more effort from the FAA to evaluate. even in the cases where an operation may seem simple, there are more opportunities for an evaluation to turn into an expected territory with a more complex method. In the other hand, lower fidelity approaches typically do not require the same level of effort, but usually result in more restrictions to the operation. This is because low fidelity analysis introduces assumptions that are conservative to the answer result. These restrictions could be in base of limitations in launch azimuth, larger hazard areas, limited visitors, time and date of operation. Depending on the launch location, the surroundings may make some of these restrictions not practical. One important note here is that there is no absolute metric of fidelity when one compares the fidelity of two approaches, since both of these come with their own biases and uncertainty. An analogy for this discussion is featured in the green box that compares the practicality and cost of two different saw approaches. The hand saw is relatively cheap, but restrictive and unsafe. The circular saw may be more practical to use and safer, but it's more costly. So it's a decision of the applicant to balance those two constraints. Now we go into an example featuring C1 to C3 elements. Let's assume a fictitious LAN provider called Space Brujas, or SB for short, who has submitted a methodology description of 450.117 for the launch vehicle name Broomstick 1. SV uses a in-house 6DoF simulation tool called WizardSim. This is a closed-loop GNC simulation coded in MATLAB and Simulink, consisting of collection of simulation models that represent sensors, actuators, vehicle dynamics, and flight environments. The high-level process of developing normal and dispersed trajectories is shown in the figure in the slide. Trajectory outputs from the trajectory optimizers that incorporates mission objectives, the environment and vehicle parameters is used in the 6DoF simulation, accounting for wind conditions to construct the normal trajectories. One of the things that SB provided us was a section of their slush methodology. That's one of the many sections in their nominal trajectory methodology. And we will take a look and see what they submitted. In this document, hopefully everyone can see it, SV provides an overview of their methodology approach for the sludge model. Again, this is just one small section of their whole methodology, but in order to get the idea across of the level of depth, content, and rigor, we are using just one small part of the methodology approach that deals with the modeling of sludge. The abstract discusses the motivation behind modeling sludge and the importance that it has on the dynamics of the system, and the conceptual approach they have chosen to use, which is the equivalent spring mass damper approach, and provides a scope of where the model is applicable, only for small field displacements under normal flight conditions. As stated here, modeling the motion of propellant is very important as it affects the dynamics of flight, center of mass, moments, and inertia. There is clearly a defined set of variables in the nomenclature. It is important to note that the documentation should be formatted to meet the standards of technical reports. Should be free of grammar errors, cross-reference, continuing revision, history, abstract, nomenclature, label figures, named equations, conclusion, reference, etc. SB has chosen to introduce assumptions. Assumption section, there is. Has chosen to introduce assumptions and justifications first, which makes the more logical sense, since the assumptions typically shape the color and flavor of the analysis. To meet requirements of 450.115C2, SV chose wisely to put the assumptions and justifications in an easy to read and easy to locate table. Here they provide the assumptions and corresponding justifications that are essential in the conceptual understanding of the methodology. These assumptions include assumptions that the scope of the methodology apply only to small displacements, and assumptions that simplify the mathematics that represent the physical phenomena, such as negligible mass change, and assumptions to the statistics used to represent uncertainty based on observation of similar vehicle sludge models in flight history. And then the next portion.
So yeah, I think I'll just add some of these things, we got some very important assumptions that actually, to justify that, is like this reference 6, and you'll see at the bottom is a whole it's a report that actually, looking at NASA, why is this assumption a valid one? Where did it come from? And that's usually where, a lot of these assumptions will actually be justified, is from some external source. This is why it's often, maybe more convenient to reference an existing technical method that already exists that's out there to go through that, because otherwise you're going through and figuring out why is this assumption a valid assumption. We've also learned that figuring out what your assumptions are is super important to justifying your methodology, because we have in multiple evaluations found that a key problem is that there was an unstated assumption, which then as we dig into it is not correct. And then that can invalidate the entire methodology. The approach is just wrong because it doesn't work in the situation that you're using. The scope of what your method is applicable for and what the assumptions behind it are really important to making sure that it's the methodology that actually applies to the scenario that you're trying to model. Okay.
Very good. Then we have SP's 450, 150 C1, Scientific Principles and Statistical Method section. Here we start to see figures depicting the parameters of the sludge model, and overview of the describing the spring mass damper relation to the model, providing a clear link between the overview and the elements of the model. SB provides references supporting claims that the mechanical model and dependencies come from established scientific principles accepted widely in industry. The reference help a reviewer verify this claim and inspect the model should he or she choose to. Remember that we discussed the scientific principles are referred to knowledge base on the scientific method, such as established fields of physics, chemistry, and engineering. There are plenty of published research and study addressing all of these fields in a sludge problem, not only in rocketry, but also in transport of liquid tanks on land. NSV has effectively leveraged that work. And let me continue on in the last sentence of the paragraph. I'm going up, Dr. Larson. I think one more. There. And the last sentence of this paragraph, FC declares the inputs that go into the model, mainly the geometry of the tank and characteristics of the propellant, followed by a set of accepted equations and the methods of how they are implemented into the model, and the expected outputs of the model, which is the frequency, the sludge mass amount, and the location of that mass, and the damping with baffles when the liquid is excited. From which these outputs, one can determine the forces and moments and add that to the 6-step simulation using a predefined uncertainty distribution. So I think I'm done with that section, Dr. Larson, unless you want to make any comments.
No, I think that's good. Yeah.
Okay. For C3, the rationale of the level of fidelity, SB notes that there is a small bias in the spring mass damper linear model that is used, claiming that the error in the magnitude is roughly around 15%, given the assumptions of a small liquid displacements. This value was deduced by a comparison of their vehicle tank design to another launch providers and the testing that the launch provider performed to validate their modeling approach. To justify that this model comparison was appropriate, as we compare the two tank dimensions and propellant use and fuel ratios and characteristics, and found that there is enough favorable similarities. As the image of the two tanks, there it is. In the image of the two tanks are virtually identical. SB provided a reference to documentation of the test performed by the other launch provider, which is NASA, and briefly described their setup in this section, providing the references for any further detail that we may want to evaluate. NASA found through their testing that their analysis using a spring mass damper setup similar to what SB is using results and within 5% of the sludge frequency based on their test results, and within 50% of the sludge mass and hinge point location, values which SB will use in their dispersed set. If we continue on down to Dyson. Okay. Yep. Finally, very end. There you go. Finally, SB makes the reasonable claim that accounting for the uncertainty in the dispersed trajectory set is appropriate given the small propellant displacements expected during the normal flight conditions, and that the ring baffle introduced in the design provide the damping required to meet the stability requirements and prevent instabilities of the control systems to an acceptable level to meet mission objectives, while not introducing errors in position that affect the risk analysis. So here we have inputs, outputs, and a relation to real life, how uncertainty affects the result, the position and velocity of the vehicle, and SB makes a reasonable claim that does not affect the risk. And finally, we have the references, which is very important to note. Again, the references are very important because we can use them to evaluate the approach and rectify any claims made in the assumptions or in the modeling. Dr. Larson, do you have any comments you want to?
No, I think you did a nice job. We're still working on this example a little bit. We do want to distribute it as well. You might have noticed there's still some comments on here. It's not easy. We understand it's not easy to write these methodologies, and that's why we see, it's going to take some iteration. It's like when you if you submit a journal article, there's peer review, and that peer review, my experience, makes it better and identifies things that you just can't see. So if you can get it, first get it to be really a quality and comprehensive enough, then usually it's not an extensive iteration process. But the goal of today is to show you the kind of level of depth and detail and the things that we are looking for, recognizing there's still going to be, it's very hard to make a perfect methodology submission, just like it's very hard to make a perfect submission to a technical paper on your first attempt. I think I think it's actually, although we're going to cover C2 to 4 next, there is a question here, and I think it might as well answer. Maybe we have other ones now.
Yeah, that's a very good idea. Thanks.
So when the question is, when submitting a means of compliance document for FAA review, would you be willing to review a partial submission that contained a list of assumptions and justifications first? Then we can reach agreement with the FAA on the list of assumptions before developing the rest of the MOC documentation. Well, first I will say, this is really methodology. Methodologies are one way of a means of compliance, not the only way. So just a clarification in terms there. But also the assumptions are related to the methodology. So we certainly would be happy to discuss those, but it's different question to say, you know, what are the assumptions of this methodology? Then are the assumptions made valid for the scenarios that you are intending to apply the methodology? And it's important often when implementing a methodology to make sure that the assumptions are met. You know, for example, in this slosh case, it would be important to have a constraint that if it's producing magnitudes of slosh that are outside the range in which these assumptions work, then something's gone wrong and it's no longer the right methodology to apply for this situation. So yeah, I think we're happy to take a look at subsections of a methodology and provide some feedback. But as I say, the assumptions are, this is what this math, this engineering approach, the assumptions that for the scenarios for which it applies. And it's a different question to say, is your operation fit within those assumptions, your vehicle, your mission? Yeah, so I think it could be, I mean, so that's what I said, I think we could look at something. Again, we're not gonna, I will say, we're probably gonna not prioritize a partial methodology if we have, you know, we tend to prioritize materials that are more comprehensive and appear closer to meeting requirements. As you'll see in the third section of this workshop today, we have now a process to filter, to do a preliminary review before something is going to go to an expert. And we want to get something that's, you know, the further along that something is, that's when it will actually get to going to an expert. Or it's, you know, we have a limited throughput, so of course we prioritize the things that are more complete over the stuff that's less so. Okay, other questions at this point, or should we go on to, we're probably a little bit behind schedule actually too, so. Okay, go ahead, Luis.
Okay, so 451.15C4 is about the evidence for validation and verification for 451.1G. We have identified 3 processes that benefit from B&B. Process B&B describes the structural and operating procedure as a whole to achieve the level of fidelity that is sufficient to be used for the risk analysis. This is a record of traceability of the input data source through all the aspects of the transmission, storage, and processing of its final form. It also includes the configuration management that is applied over the life cycle of the process to provide visibility into the control changes of performance to the functionality and physical characteristics, and include a well-constructed or well-controlled process for improving that modeling base in flight experience, like a post-flight review. It also includes computing system safety items that define critical safety for 401.7. The second process that we see a value in B&B is obviously the modeling and simulation. And that addresses if you have built the right software and if you have built it right. B&B of the mathematical model that includes the mathematical equations, any boundaries, initial conditions, any data needed to describe the conceptual model, which is implemented into a computational simulation model that is the actual code. And the rigor of B&B depends on the level of criticality of the model. Typically, an IB&B will not be necessary for some of the tools or some of the submodels on the tool, but it's definitely an option. Another process that we see value in verifying and validating is user qualifications. Your process only as good as whoever uses it. This ensures the proper use of the process and of the models to reproduce a function or action that's repeatable and produce the same result. Operator qualifications and recertifications are important, and those qualifications may change with time as your model progresses through the life cycle. And that is where verifying and validating those qualifications and recertifications is important. That should include any experience assessments, qualification and experience assessments for the people developing, testing, or using that software or process, including the maintenance, the operations, the result analysis, the training, and any error reporting when something is found wrong with the process or the model. It is intended to identify personnel who are likely to perform the process successful, and defines and should define the roles and responsibilities for every user within the process, and should provide also a minimum set of descriptions and requirements of what constitute that operation and the qualifications for that operation and user. It includes, obviously, safety critical personnel qualifications under 450, 149, especially those that perform day of launch activities. And we have some references here. DODI 5161 provides a good overview of BMB. And also NASA standard 7009 and the handbook 7009 provides a good description of accepted modeling and simulation practices. And the link is provided in the slide. Next slide, Dr. Larson.
Yeah, I think I'll add, we've heard some requests from industry for more details, more references for what V&V is, and we definitely want to work on that. So this NASA handbook that's here is a start to that. But we understand, we hear that and recognize that, and want to point out that part of the process, the methods include not just the software or the not just the scientific principles. That's only a piece of what's going on here. But how do you make sure this is a safety analysis, that the safety analysis is actually the right safety analysis being done right? And that's where the verification validation includes, can include processes, procedure documents, and so forth. And it depends on the complexity of the analysis and the conservatisms built in as to how much V&V is appropriate. But another example, if you're doing a countdown analysis, that should follow a well-defined procedure, and there'd normally be a dry run to do that. That validates that your processes are in place and that they all can be accomplished.
Very well. Next slide deals with benchmarks and asks for the applicant the extent from which the benchmark conditions are comparable to foreseeable conditions of the intended operation. A benchmark is independent good or acceptable standard against which your process or model results can be made to check a product, services or systems intended for that purpose. It describes a situation where the modeling approach has been compared to, say, an empirical data set or other modeling approaches. That is your in-house SIG stuff to a industry accepted SIG stuff simulation like POST. It provides context and is critical element for an analysis to identify best practices. It can help identify issues and improvements in your process and your technical development of the software. Conditions should be compared to the intent of the scope of the methodology, discussing the regimes where the model is closer to or further from that benchmark. Not all benchmarks are going to be exact to your operation. So you need to describe why it is comparable, and if any of those discrepancies make a difference in your modeling or results. Benchmark should run in parallel with the methodology, bringing standards and best practices from elsewhere, things that you may not have thought of, while the methodology preserves knowledge generated within your organization. So you're comparing your knowledge to someone else's knowledge, and then finding discrepancies or similarities, and then that usually provides a confidence in your modeling approach or process. Yeah, if an appropriate benchmark is used, then and you may end up making erroneous conclusions. Again, no amount of benchmarking is sufficient to verify accuracy. All models and processes come with their own set of assumptions and uncertainty. Benchmarks, however, increase that confidence, but cannot alone determine that the approach or model is correct. Regulations includes the extent to which, that is the call out in our FSA of section of 451.15c. It is so because the FAA acknowledges that could be cases that are so unique that relevant benchmarks are unavailable. But however, an applicant is still expected to address and provide some reasoning to the extent to which those benchmarks, if any, were used relying on the best available data at the time of the analysis. And the lack of a benchmark, an applicant may discuss the level of conservatism included in their approximation. Dr. Lawson, you want to add anything?
No, that sounds good. Thanks.
This is 451.15c6. This is the extent to which risk mitigations were accounted for in the analysis. This describes how mitigations are incorporated in the flight safety analysis process and methods. Examples such as flight safety system, hazard areas, launch commit criteria may not always be applicable to a particular methodology, but are options for others. Mitigations may include those described in the functional hazard analysis. Mitigations include redundancy of design, conservatism used in analysis, FSA mitigations should be correlated with FSA elements. FSA produces mitigations such as flight safety analysis, which are used in the downstream analysis. Arguably, they are the most important products of the flight safety analysis. Regulation, just like with benchmark, includes the statement of extent to which, as the FAA acknowledges that there could be cases that are so unique that relevant mitigations are unavailable or are not applicable. Applicants are still expected, again, to address and provide some reasoning to the extent to which risk mitigations were used, relying on the best available data. Any input, Dr. Larson?
No, I think, yeah, we'll get to the example and I think you'll see more.
This is example of 451.15c, 4 and 5 and 6. Again, we are using our fictitious launch provider, that's Space Brujas, who has submitted a methodology description of 451.17 for the Broomstick 1 launch vehicle. As mentioned before, their in-house simulator has been coded in MATLAB, Simulink, and is used to develop a full guidance, navigation, and control software solution, especially designed for the launch vehicle at hand. So to meet requirements set by 451.15, SB provided an IV and B report of their 6.0 simulation, which attempts to meet the requirements under 451c4. Benchmarks using a post2 intended to cover 451.15c5 and a list of risk mitigations, and based on trajectory design and simulation testing. And we'll see how they did. We can go ahead and move into the document. Thank you, Dr. Larson. Appreciate it. So this is their submission. For the software portion, their approach, they opted to do an IBMB of their in-house 6-stuff model by an independent entity called TestRS, and the results are documented in reference to. And they provided to the FAA that reference for review. This IBMB document is comprehensive enough, discussing the requirements defined in the testing procedure for all static and dynamic models and the corresponding inspection, verification, and validation. SB included in this sample here, shown a table which clearly outlines the area that was reviewed and description of the task and the findings along with any recommendations. Again, this is just a sample of the document that was referenced earlier. Very well. But SSB also recognizes in this second paragraph that an IBMB is not enough to comply with 115C4 for a process that has a long life cycle. They noted in this section a plan for verifying and validating updates to the simulator based on software quality control documented elsewhere. And in this plan, SSB will implement test procedures using repeatable and prescribed test environments to support the testing of the whole simulator tool during the verification activity. And this will be accomplished with task cases with different levels of complexity, exercising the full equations of motion. This approach is based on NASA's recommended approach for verifying 6-stuff flight vehicle simulations and is referenced for the FAA to review. We can look it up and provide a evaluation based on that approach. And there's extensive verification and validation of NASA's approach in their website. This includes, their NASA approach includes a set of test cases using multiple vehicle models. A test case using multiple gravitational models, a test case using multiple atmospheric models, and a test case using coordinate system transformations from a different number of coordinates. This provides a very rigorous check of their verification of their model based on something outside of their process, but that's included in the process is referenced so that we can take a look and verify that that is an applicable approach. In addition, if you look at the next, okay. In addition, SB summarizes their software control to ensure that only correctly released and authorized version of the software are in use. As you may imagine, sorry. Yeah, as you may imagine, as the life of the program progresses, there will be updates to your model where you're adding more attributes or characteristics, and having a software controlled process is very important. That details the approach that is taken to document how that model is processed and what's available for a user to access. Very well. Then we go into 451.15C5, unless Dr. Larson has any inputs.
No, looking good.
Okay. Okay. 451.15C5 is the extent to which benchmark conditions are comparable to the foreseeable conditions of the intent operation. SB benchmarked the entire trajectory model against NASA's POS2, which is widely used and has gone through rigorous levels of validation and verification, and is therefore a viable benchmark for the 6-stuff simulation. SB provides a reference that describes in detail how they configure both programs to run the same trajectory to allow them to perform a direct comparison of the two 6-stuff solvers, and noted that they were run independently by different operators. That's very important because that allows for more confidence, having two different engineers looking at two different programs coming up with the same result. Lastly, they provide overlay and comparison of the key outputs, as we will see in the figures. A little bit more, Dr. Larson, to show the figures. Okay. Okay, there you go. They're providing overlaying comparison of the key output parameters from the two simulations, which include planned Jettison body dispersion ellipses, showing no meaningful difference in results, as shown in that one figure that just passed by, as well as a plot that tracks position error and cross range and downrange distances with respect to time. This is convincing evidence that their model accurately integrates the equations of motion and is a valid base of this benchmark. Any inputs, Dr. Larson, before we move on? Okay.
No, I think it's great.
Now we go on to the next element, the extent to which risk mitigations were accounted for in the analysis. The risk mitigation strategy for SV is to leverage the capability of the vehicle in the process of designing the trajectory to allow for maneuvers to avoid exposing population. The trajectory design process has enough margin in the propulsion and control to allow for dog legs to correct for launch azimuth and place the vehicle in a corrected azimuth and inclination to meet objectives after launch. This is conceptually depicted in the one figure that we barely can see. If we can pull up a little bit more, Dr. Larson.
Mm-hmm.
Okay, so this is so that any trajectory failures do not place debris in the near island that you can see near the launch site. Another risk mitigation noted here is a mission redesign of the trajectory for the day of launch, accounting for the latest atmospheric conditions to ensure that structural limits are not compromised. Navigation control is maintained and vehicle flight plan is achievable. The detail of this approach is documented in another section of the document, or it could be in another document, whether this is document, another document, or a reference. This type of update is valid risk mitigation, as it will reduce the likelihood of failure due to atmospheric effects and ensures that the measured launch site conditions are within the variable set that was analyzed in the flight safety analysis, for which launch hazards have been generated for land, air, and sea. Next, yeah. The next risk mitigation noted in SV's section of 451.15C6 is the HETO testing. This is associated with testing the hardware based on commands from the flight computer configuration files that eventually could lead into adjustments to the simulation resulting from the behavior of the hardware and the response of that hardware. And lastly, the last risk mitigation noted by ASB is a post-flight review process, which is a valid risk mitigation. Post-flight reconstruction of a flown trajectory using actual vehicle telemetry evaluated against the simulation could lead to improvements in the simulation, particularly related to configuration files and input tables. One example that was noted here is the collection of aerodynamic data from real flight, which would lead to reduction in aerodynamic uncertainty. And another example noted in this section is updates to the response of the propulsion system, resulting from improvements in the design from for the life cycle of the license. A post-flight review process is a good thing, and it's valid risk mitigation, as it ensures there is a continual process improvement to address inconsistencies in the model of normal trajectory generation. And then of course you have the references. That is also important to have in the document. Any comments, Dr. Larson?
No, I think one, just to point out that, this is thinking about a methodology that's going to last through a life cycle, over a duration. It's not just we're doing it's anticipating that the process will be improved and that there will be lessons learned. As any good process has, you learn from what you've done and make it better going forward.
Any questions? This is the end of the section.
Yeah, it was asked in the chat whether these examples will be distributed, and yes, that's our plan too. We want to do some more editing, and but we do plan to put them out there. So for post them on the website so everybody has these.
I think using 117 as an example is really useful here because it gives some examples of where does the FAA stand on regulating mission assurance versus regulating safety. So for example, if I need to get a slosh model approved by FAA, in my mind, that is something that is only affecting mission assurance. If I get the slosh model wrong, my launch vehicle fails. But what is the FAA stance on mission assurance versus public safety?
So if your launch vehicle fails, it always, that is a public safety implication, whether it's, there's, it affects, the failure of a launch vehicle affects the determination of hazard areas, which determines where you're keeping people out. There's not like there's a, if you have something falling back to Earth, that is a public safety issue. If you're going outside of where you intended to fly, then that's a public safety issue. Maybe you'll still be able to, succeed and it won't be a mishap, but usually, or, you'll still be within the limits of the useful.
So your stance is that anything that could cause a failure, even if it has a hazard
Still be a
control
mishap.
strategy, should be
within limits of the useful mission, but it's outside of where you. Or a meaningful effect on. I would say in general, yes, it needs to account for all reasonably foreseeable failures.
Account for, but it sounds like FAA is saying you need to accept.
Well, I think, just for, you can make an argument why, one of the things in the normal trajectory stuff is anything with a significant influence on your development of your normal trajectory dispersions. Where your vehicle is going to be and where you.
Sorry, you broke up a little bit there. Or is it me? Did anybody else lose Dr. Lawson?
No, it sounds like it's Dr. Larson.
Okay, I am back now, I think. Can you share my screen again?
Okay, so this section talks about we're introducing our checklist, which has a list of topics that we see as important and a methodology. And these key discussion topics are based on 450-115C and the applicable requirement. That is, of course, associated with the validity and assumptions and fidelity of the submission. And to help our evaluation and more effectively manage our resources, we have compiled this list of key discussion topics derived from a conceptual concept and objectives of the methodology that should be considered and addressed for each flight safety sub-analysis of the regulation defined in 450-117 through 451-135. Well, we use this list of key topics as a checklist to determine if an applicant's methodology submission is complete enough to begin an evaluation. And we will show you shortly an example of that. We will provide this to applicants pretty soon. We are still getting it to the process, but we'll be releasing it and will probably be available on the website. Next slide, thank you. This is an example of 450-131 POF section, and it's the checklist, as I mentioned, that provides a number of discussion topics that we expect from this methodology. On the left, we have the requirement of the probability of failure analysis for reference of the discussion, and to the right, we have a checklist pertaining to this methodology. The first three sections here on the top are general and intended to set a foundation of the analysis. These include an entry criteria, a scope, and list of prerequisites, and identifying what the analysis intended to cover. And there is availability of the sufficient and desired data from an external source and or from a flight safety analysis section to begin that analysis. In the case of POF, examples could be for a scope declaring any limitations to mission profile or phase of mission type. And for entry, identifying a suitable list of similar vehicle flight history with enough detail to determine failure causes and failure modes. For flight safety analysis prerequisites, identifying that a functional hazard analysis has been completed and approved. Identifying applicable mission phases and events from normal trajectory analysis. The other three sections here define a list of common data products that are usually produced to build data sets for computation and carry with them some assumptions and logic descriptions with that conform to 450C1 and 415C2. The first section, data parameterization, describes the factors used to classify the group vehicle data available for the analysis. This is designing that database that will be used for the analysis. Data load refers to the process of selecting what data to upload into the database and should account for updates of information from new flight. And data selection is that database query logic capability in order to departmentalize what vehicles apply to yours and what phases of flight are applicable. Again, the checklist now focuses on common list of calculations that are typically performed when estimating probability of failure to meet 450-115C1 and C2. Vehicle analysis deals with flight events, phases, decomposition analysis, which is the breaking down of a mission into exclusive phases or flights between event milestones and vehicle flight sequence, like engine start or shutdown. After the decomposition of flight into phases, the next step is identifying reasonable failures for 450-131B within the phase, within that phase, based on the functional hazard analysis and mapping or grouping those failures into failure modes. The next section is all about data analysis, using vehicle and sample vehicle history to develop a statistical outputs and uncertainty. What we are after here is a discussion of the statistical method used to incorporate those sample flight history for 450-131C and your vehicle history. The assumptions and logic descriptions associated with that integration is important. This also goes into the decomposition of the vehicle analysis and how POF gets applied across phases and events, whether it's by stages or a top-down level approach. The next step is discussion of the mechanisms that allocate to lower levels for 450-131D and particularly to the individual failure modes that turn those then into time rates, likelihood of failures as a function of time. Typically that is per second. And it also goes into calculating what the differences of observed conditional rate are as for 451.31e. Unconditional rate is the probability of failure rate based on phase of flight occurring given that previous phases of flight was completed successfully, which is the final product that goes into 451.33 and 135. The other items are that are expected as discussions are the level of fidelity to comply with 450.115b and C3. These are the benchmarks to validate results for 451.15c5 and any risk mitigations to comply with 451.15c6. And lastly, any verification and validation for 451.15c4, particularly related to software. Any other comments, Dr. Larson?
No, I think I'm interested in questions here, I think.
Okay.
Yes, I hope you see that, these checklists are, one of the things we're trying to do with them is help us to become more efficient in our reviews. So that, we trying to decompose the requirements into lower level things that we expect to see. As noted at the beginning of the checklist, that this is how we've decomposed it, but there's definitely some discretion that gets applied when looking at these, and it's certainly possible that not everything will need to get covered here, but somehow these are the topics that are normally necessary in order to demonstrate compliance with the requirements, but perhaps not always. It still goes back to what is actually in the regulation as the requirements here. Okay, so there's a question. I recently had to use these checklists with no instructions and found that the wording could be improved to clarify how to fill them in. The custodians of these open to feedback from the users. Definitely, we're open. Our goal here is to eventually get these into advisory circulars with explanations of what's going on here, so that they can be understood. Because they're intended to be a job aid, and we recognize that for us, we recognize that they would be also helpful for applicants to see, and that would make it even better. But we came up with them as internal job aids for us to try to do our jobs more efficiently. And I think that question, just for your information, came from one of our internal contractors. So not from, I don't think applicants yet have these checklists. We want to get them out there, but they're still getting tweaked before they're ready to go out.
Well, if there are no questions, this is the end of the main workshop. Our next step is to edit the workshop, this PowerPoint slides and the examples, and based on any feedback that we got today. And we'll provide those when those are finalized. There's no additional questions, then this is the end of the workshop. Thank you again for participating. We appreciate you making the time to join us today. Thank you, Dr. Larson, for answering those questions.
Thank you, Luis. Excellent job.